Last episode, you saw why backprop is cheap. Reverse mode hands you the whole gradient in one backward sweep for about the cost of one forward pass. So you have the gradient. Now the obvious move is to take a step. But here's the question. Nobody asks early enough. The gradient of what? The gradient of the loss over your whole data set? Or the gradient over one example you happen to grab? Those are different vectors. One is expensive and smooth, the other is cheap and twitchy. This episode is about that twitch, vanilla stochastic gradient descent, and why a path that looks like a seismograph still gets you to the bottom. Start with the honest slow version, full batch gradient descent. You compute the loss on every single training example, average it, take that gradient, step downhill. One step uses the entire dataset. The misconception here is that this is the correct optimizer and everything else is a shortcut hack. It's not. Full batch GD gives you the true gradient of your training loss, but the true gradient of the training loss is itself just an estimate of the thing you actually care about. So exact is already a comfortable lie. Now the cheap version, stochastic gradient descent, batch size 1. Grab a single random example, compute its gradient step. You think next word will be approximate, and you'd think an approximate gradient must point in roughly the wrong direction. It doesn't. The single example gradient is unbiased. Average it over all the examples you could have drawn, and you get the full batch gradient exactly. It's not wrong on average, it's just loud on any one draw. Here's the picture that fixes the intuition, a target with dots. Full batch GD is one dot thrown precisely into the bullseye, the true direction. SGD is a fistful of dots, each landing scattered around the bullseye, but centered on it. The common misconception is noise means bias. No, the scatter has mean 0. Throw enough dots and their center is exactly where the careful dot landed. Each individual throw is just a noisy sample of the same aim. So why does the loss curve look so different? Because you plot every step. Full batch GD's curve is one smooth glide because every step used the same average signal. SGD's curve is jagged because step 41 saw an easy example and the loss dipped. Step 42 saw a hard one and it bounced back up. The misconception is that a bouncy loss curve means the optimizer is broken or diverging. A bouncy curve at small batch size is expected and healthy. It's the variance you signed up for, not a bug. But the noise isn't free and it isn't pure cost either. Where the careful GD step can slide straight into a sharp, narrow minimum and get stuck, SGD's jitter rattles it past the narrow traps. The misconception worth busting: people call SGD noise unnecessary evil. In practice, the noise is a mild regularizer. It nudges you toward flatter, more forgiving minima. The same twitch that makes the curve ugly is part of why small batch training often generalizes better. Two knobs control the twitch and people confuse them. The learning rate sets step size. The batch size sets gradient variance. Bigger batch averages more examples, so the gradient is quieter, the band narrower. The misconception: just lower the learning rate to smooth out SGD. Lowering the LR shrinks every step, including the good ones. It slows you down without removing the variance. If you want a quieter gradient, raise the batch size. If you want a smaller step, lower the LR. Different dials, different effects. So the trade is laid bare. Full batch GD, one expensive, exact, smooth step per pass over the data, beautiful and slow. SGD batch 01, thousands of cheap, noisy, jagged steps per pass, ugly and fast. You don't pick one because it's right. You pick where on the spectrum you sit by choosing a batch size. Next, we'll see what happens when even SGD's average direction is systematically bad. When the landscape itself fights you in a long, narrow ravine, and a smarter step has to remember where it's been. Open 06 SGD versus GD.py. We define a tiny logistic regression toy, a handful of 2D points, a binary label, sigmoid output, cross entropy loss. Then we run 2 optimizers on the same problem from the same start, full batch GD and SGD with batch size 1. We log the loss at every step for 100 steps, and we also track the running variance of the SGD loss, so we can shade the +0 12 band, 1 figure, 2 curves, same destination. First the toy. Make toy returns X, 8 points, 2 features, Y, binary labels, and an initial weight vector BV0. Nothing fancy. The point is that this loss is convex with a single minimum, near loss 0.05, so both optimizers must land in the same place. If they don't, the bug is ours. Loss and grad WXB YB is the shared engine, sigmoid of XB at W, binary cross entropy against YB, and the closed form logistic gradient XBOT at P YB, len YB. It takes a batch X bay, pass the whole X, and it's the full batch gradient, pass one row, and it's the single example gradient. Same function, both regimes. That's the whole unbiasedness story in one signature. Run GD is the smooth one. Loop 100 steps, compute the gradient on the entire X. Step W O calls LRG, record the loss. Every step sees every example, so the recorded loss falls monotonically, 230 to 0.05, no bounds. Run SGD is the jagged one. Same 100 steps, but each step draws one random index, computes that example's gradient, steps. We record the loss on the full set after each step, so the two curves are measured on the same yardstick. The recorded values jitter inside a band because each step optimized for one point, not the average. Variance band turns the jitter into the shaded region. It returns mean plus 0.12 at each step, the half width pulled from the empirical spread of SGD's late stage loss. This is what gets drawn as the translucent envelope around the SGD curve, the visual proof that the noise has a fixed scale centered on the GD curve. Print the headline. At step 100, GD sits at 0.0543, SGD at 0.0480, inside the plus 0.12 band, same minimum, different texture. That's vanilla SGD, unbiased, noisy, cheap, and good enough that it's still the backbone of everything. Next episode, we add memory to the step, momentum, and watch it roll straight through a ravine that makes plain GD zigzag itself sick.